Hello everyone, welcome to watch the video tutorial of the Traverse Assistant. Today, we will mainly talk about the newly added function of the Traverse Assistant app for triangulation elevation measurement, which is Elevation Traverse. This video is mainly about how to use our trigonometric elevation line function to create our project and station, demonstrate the process, and then demonstrate how to measure on site after creating the station on our mobile phone. Finally, we will talk about our elevation line, which is the data of trigonometric elevation field observation, after completing the measurement and returning indoors, how to perform the adjustment for indoor work. If you are interested, please let us know. You can go and watch the corresponding parts according to your own needs. Firstly, let me give you a brief introduction to our elevation line function, as well as how to create projects and triangular elevation routes. Some users may not be clear about what triangular elevation is. Here, I will briefly introduce it to you. As you can see, trigonometric elevation is a method of measuring the height difference between 2 points and the elevation at a fixed point. When the terrain in the survey area is undulating and leveling measurement is slow or difficult, trigonometric elevation measurement can be used. If you see this, you can see the trigonometric elevation measurement method. Its purpose is to measure the height difference and the leveling measurement we usually do. In fact, the final data obtained is the same, all for the purpose of calculating the height difference, while triangulation is mainly suitable for less suitable applications. Places for leveling, such as mountainous areas, which are very steep and cannot be pushed up by leveling, can use trigonometric leveling. Secondly, in some cross-river leveling, this triangular elevation is also used to observe a height difference on both sides of the river, which is one of the observation purposes and an applicable area of our triangular elevation. We now open the Wire Assistant app, which is the project interface of our Wire Assistant. In this area, we click the plus sign in the upper right corner. You can see that if you create a new project below, it will be divided into 3 types. The last type is a special elevation wire type project developed by us for triangular elevation wires. This type of project, there are significant differences between the new project interface and the other 2 types of triangulation and connection measurement interfaces. Here, I will also briefly introduce the areas that need attention on this interface and what these settings represent. In the interface of the new project, the software is divided into 2 ways of setting up stations. One is to set up stations at intervals, and the other is to set up stations at each point. What do these 2 mean? I use the electromagnetic wave ranging elevation traverse measurement in this national 3rd and 4th class leveling specification. In this chapter, we will explain the content to you. In fact, this chapter is a special explanation and requirement for triangulation in the national 3rd and 4th class leveling standards. In this chapter, you can refer to chapter 9.22. Which mentions that elevation lines can be arranged as instruments for opposite observation at each calibration point, that is, the route of setting up stations at each point. It can also be arranged to install instruments at every lighting point, which is the route of setting up stations at intervals. What does this mean? I will demonstrate it with a picture. Let's first talk about setting up a station at this interval, which is the second scenario. It is also the default method chosen by our software when creating an elevation line. Assuming we want to observe a height difference between 2 control points, which may be a control point. These are 2 control points, and the target positions of the 2 control points are the same. Of course, the 2 points may be control points or encrypted points, which are actually similar to the plane we usually push, such as a branch line or a closed line. Starting from one control point and closing to another, it is pushed along the route rather than just a single station measurement. So in this case, you may be observing control points, or you may be observing encrypted points. What does it mean to set up stations at intervals? Setting up stations at different points, some of our friends may be accustomed to using the middle method, which means that when we measure at 2 target points, we do not call them any points, but rather 2 targets. We directly set up our prism on these 2 targets, a fixed height prism, and our total station. We can set it up at any place, not at a control point, but at any place where we can see both targets simultaneously. When we observe, we also observe the position of our total station and the height difference with this point, assuming what height, and then the height difference with this point. In the triangular elevation line, we follow the direction of the line's movement. Usually, one of them is called forward view, and the other is called backward view. It actually means the same as pushing a plane line or leveling. One backward view and one forward view. We only need to observe the height difference between the center point of our instrument and the two target points, and the accumulated height difference is actually the height difference between these 2 points. In this measurement process, the location where the instrument is installed actually indicates that it is temporarily installed. This point is only used once, just like when we push the leveling line, it is randomly set up and left after use. Therefore, this place is an arbitrary point. Generally, when using the intermediate method for observation, the instrument is high and can be measured or not measured, which is our method of setting up stations at intervals. This is a method of measuring trigonometric elevation using the intermediate method, while our other method, which is in the standard, is to observe objects by aiming instruments at each aiming point, that is, setting up stations at each point. What is this observation method? Assuming these are our two targets, which could be control points or encryption points, our instrument is directly mounted on the target we want to observe, and then another point is used to mount our prism. In this way, by measuring the height of this instrument and the height of the prism, and then observing the height difference between the center position of the instrument and the center position of the prism, we can directly calculate the height difference between the two targets. This is how we set up stations at each point. If we set up stations at each point, according to your project requirements or accuracy requirements, it can be observed unidirectionally or in opposite directions, because it is similar to the back and forth measurement of leveling. We can observe at this point according to the direction of the wire, so that the height difference between the 2 points can be observed. Then the next time we are at the third point, the instrument can be directly installed at the third point, and the middle point can be left unused. Then, we can observe the height difference. If the project requires high accuracy, we need to conduct opposite observation. That is to say, we need to set up another instrument here, then set up a prism at this location, and observe the height difference between these 2 points. In theory, the height difference calculated between these 2 points should be equal, but the positive and negative values are different. Of course, there will definitely be some differences in actual situations, but the height difference between these 2 measurements should be equal. The discrepancy value cannot exceed a certain limit, and there are also certain requirements in this specification. In order to improve the observation accuracy of our wire during round-trip measurement, if your accuracy requirements are not high, then only one observation is needed, which means we will set up one less station in this area. In the software, it also supports this observation method. For example, if you set up a station at each point, we can observe it in either a unidirectional or opposite direction. If we observe in a unidirectional direction, it means assuming 3 points, I only need to observe 2 stations, observe 1 station here, and then observe 1 station here. This way, we can determine the height difference between the 3 points. If we observe in an opposite direction, we need to set up one observation to observe the height difference between these 2 points, and then set up a second observation, observing the height difference between these 2 points and the height difference between these 2 points, and then setting up a third observation of the height difference between these 2 points at this point, which is 3 points. He needs to set up 3 observations and 4 height differences. This is our point-by-point setup and station-by-point setup. I forgot to mention it earlier, which is in the station-by-point setup, which is our intermediate method. There is also a method of accuracy detection similar to the round-trip measurement just now, because if we set up stations at intervals, which is the intermediate method, it is an arbitrarily set point to observe our previous and subsequent targets. When we observe, according to the requirements in this specification, when setting up stations at intervals, we should use the one-way dual measurement method, which means changing the instrument height or position at each station and making 2 observations. What does this mean? In fact, this is similar to the reverse measurement of our level, which means that when we set up stations at different points to observe the first target and the second target, after we complete the observation, we need to recenter and level the instrument or move it to another location and reinstall it, and then re-observe points 1 and 2, which is equivalent to changing the position of the instrument. In this case, the height difference between points 1 and 2 that I observed for the first time and the height difference between points 1 and 2 that I observed with instruments for the second time should be equal. Even if they are not equal, there may be discrepancies between the 2 heights due to gross errors or other instrument accuracy issues. However, this discrepancy cannot exceed a certain limit, which is required by regulations. In this software guided by our assistant, we focus on the actual observation method of the triangular elevation at this site. According to this specification requirement, we support 2 types of station setting methods. One is to set up stations at intervals and the other is to set up stations at each point. For each station setting method, we can make this adjustment according to our own requirements. For this tolerance plan, we currently follow some values in the national 3rd and 4th level standards. As you can see, there are some limit requirements here, and we have developed a limit template based on this limit. If in this actual project, the owner or design institute has higher precision requirements and can create a custom elevation line tolerance in the management interface, then our triangular elevation line project will be considered completed. We click to enter this interface, which is actually the same as the other 2 types of interfaces. We still need to enter our control points and then our encryption points here. In this case, everyone can input according to their own needs. I just input it casually here. After the input is completed, we need to create a new route. Click on New Route below. What does this route mean? The data structure of our software assumes that if we want to observe a triangular elevation line, our points 1 and 4 are control points. If points 2 and 3 are encrypted points, then in general, we need to follow the observation sequence from point 1 to point 2, then to point 3, and finally to point 4. According to this observation sequence, this is a route of our triangular elevation line. For this line, we can input all of it into this project. Then, in this project, we will enter the information of these control points and encrypted points just now. We need to click on the new route below. In this new route, we need to create the starting and ending points that we need to observe for each section. What do these starting and ending points mean? They are actually our points 1, 2, 3, and 4, which are all the points we need to participate in the adjustment later on, namely your control points and your encryption points, which are unknown points. We will select point 1 according to your observation order here, and then choose our point 2 for the end point. Alright, we will click OK below. Even if we have created the route for 1 to 2, we will see points 23 to 1 to 002. We will click the Quick Jump button to jump to this measurement interface. You can see that there is also a new measurement station below. What does this station mean? Let's click it to take a look. If you want to build a new measuring station, it will follow the type of project you choose, because as I mentioned earlier, the observation method of setting up stations at intervals and each point is different. If you set up stations at intervals, there will be an intermediate point, but if you set up stations at each point, there will be no intermediate point. For this intermediate point, which is the measuring station in the middle of us, that is, the transfer station, we will observe point 1 and point 2 separately, but here, we have a concept of a turning point. What does this turning point mean? It means that if our instrument can directly see points 1 and 2, then in the new station interface, we can directly select the endpoint, observe points 1 and 2 from the position of turning station 1, then click OK, and then click on this turning station. As you can see, our backward view is point 1, and if we look forward, it is point 2. We can go and observe them separately. However, if we are at this station and cannot observe points 1 and 2, there is a situation where there is no suitable position to display both points at the same time. We may need to turn to another station in the middle, which means we need to observe another 1 to 1, and then we can set up another instrument to observe points 2 from 1 to 1. This is actually similar to our leveling measurement. If one station exceeds my front and rear view length requirements, then I can only add a front view temporarily and then transfer to another station to measure my point 2. This is the same as its meaning. In this way, our route will be, even if all observations are completed, in this measurement interface, we currently define 4 measurement cycles, and for forward and backward viewing, they are all 4 measurement cycles. Everyone should observe the vertical angle and oblique distance of the 4 lateral cycles according to their own precise requirements. In this way, the final result of the height difference can be obtained. As for how to observe, let's take a closer look at the later content. At this point, let's go back and talk about a new interface for setting up stations at each point. In this interface, you can actually see that if you set up stations at each point, it is a bit similar to what we just mentioned. The instrument is directly installed on our point 1 and then we observe our point 2. If we check the endpoint, then I can directly observe point 2. If points 1 and 2 cannot be viewed together, then it is the same as the method of setting up stations at different intervals just now, which is to add another station in the middle. For point 1, observe our turning point 1, and then observe our second point from point 1 to 1. If setting up stations at different intervals in each point, they will be displayed in the new station interface, and the content will be different. We will also have a prompt at the bottom of this interface, and the measurement interface will also be different, because if we set up stations at different points, there is a forward-backward view, while if we set up stations at each point, it does not exist because we directly set up one target to observe the other, so there is no forward-backward view. It only has one direction, which is different from these two places. As for the observation stage, everything else is actually the same, observing the vertical angle and oblique distance. Secondly, I would like to explain to you again that when we create this new route, you can see that there is a longitude and latitude below, which is the BL of 23 to 1. In this area, it is not actually inputting a plane coordinate of 23 to 1, but requires you to input the longitude and latitude of 23 to 1 and 23 to 2. If you know this latitude and longitude, you can input it directly. If you don't know, we can click on this acquisition button. This place is our acquisition button. If we click on it, it will use a location on your phone, the GPS module of your phone, to directly locate the latitude and longitude of your current phone position. If you can see my current position, it is actually 34.7226 degrees north latitude, which is our latitude and longitude. If you collect latitude and longitude, everyone must go to the vicinity of the control point. For example, if I measure point 1, I will collect data near point 1. As mentioned later, this latitude and longitude are mainly used for correction. If you don't need to correct it, you don't need to collect it. The interface will also tell you that this is not a mandatory field, but if you want to collect data, you must go to the control point, collect an actual longitude and latitude of it. Don't fill in the longitude and latitude of this measuring station, and don't fill in the same two places. Just observe both sides directly at the location where I set up the full face instrument. Don't do this, make sure to observe. Why fill in this latitude and longitude for your two targets? Actually, we only use this latitude, and longitude is not used much. Why do we use this latitude? In fact, it is to correct the non-parallelism of the geoid. If you are interested, we can also provide our detailed information later. Teacher Sun, please provide a detailed explanation on the correction of non-parallel geoid. Then we recorded the longitude and latitude at this location. Looking back at the data we exported from the app during the internal adjustment, I opened a sample data for you to see. If you can see our software, we will record the latitude information you entered in the software, and then make corrections to these control points, which will directly affect the final height difference you obtained. Of course, if you do not have any precise requirements in this regard, you can leave it blank. Next, we will mainly explain to you that after we have completed all these preparatory work by creating a new measuring station and a new route, we will come to the measurement interface and discuss how to carry out the measurement, including the environmental information and the instrument's multiplication constant information that we need to enter before measurement, that is, on site. What kind of impact will these have on the values we actually observe? This will also be discussed in the following content. The above is the elevation traverse function of our Traverse Assistant. Continuing from the previous content, let's now go outdoors and demonstrate the field observation process of the newly added elevation traverse function in the Traverse Assistant. By the way, I would like to take this opportunity to explain to you what our actual work process is in triangulation. Friends who have read the previous content may see that our triangulation elevation is mainly divided into two observation methods. One method is to set up stations at intervals, which is the middle method, placing them in a middle position where two target points can be observed simultaneously, and then observing these 2 points. Another approach is to set up stations at each point, which means they are directly installed at control points. First, let me demonstrate the process of setting up stations using the intermediate method, which is to set up stations at intervals. Your instrument can be mounted at any point, as long as the prism is mounted at your control point or encryption point. Because this is a demonstration and we don't have many equipment, we have placed a tripod and a base at one point. We can take a photo of it later for everyone to see. We are placed on the ground, and if it is during actual observation, I suggest that you use fixed height equipment to place prisms, such as centering rods or something, whose height is fixed. Because errors such as prism height or instrument height can directly affect the final result of triangular elevation. We will now set up the instrument at a location where we can view both control points, and then open our software. On the software, I have already created an elevation wire project and a route in advance. You can refer to our previous video on the process of creating this project, which showed you how to create elevation wire types and how to create new routes and stations. Once this is created, you can directly go to the measurement interface. In the measurement interface, I have established a measurement station called Transfer Station 1, which can be understood as the turning point in the leveling measurement, which is the position where my instrument is currently mounted. This position can actually be set up arbitrarily because I used the intermediate method of setting up stations at intervals to measure and directly observe our control points 23:1. As well as an encrypted point. When creating this, I mentioned before that if you cannot observe two target points at the same time at one station, you can transfer to another station, such as Transfer 2 and Transfer 1. If you can observe it, you can directly select the endpoint, go from 23:1 to the endpoint of the route, and then click OK. In this way, even if the measurement station is created, we can directly enter the measurement interface. Observe the backward target here, and then observe the forward target, which is the oblique distance and vertical angle of the two targets. Let's start observing the trigonometric elevation. Before observation, some parameters need to be entered first, because the most important information of triangular elevation is vertical right angle and oblique distance. If the slant distance is used, it will directly affect the final calculated height difference data, so it is necessary to correct the slant distance. To make corrections, you need to input some information, including your environmental information, such as temperature, humidity, and air pressure, as well as the instrument's additive and multiplicative constants. When setting up the instrument, we should fill in the temperature and humidity information on the spot and do not add it later, because you do not know what the temperature and pressure were at that time. Therefore, when observing, we need to use a thermometer or pressure gauge to observe the actual value, and then input it into the software. For example, if our current temperature is 18 degrees Celsius and the wet temperature is 19 degrees Celsius, if there is no dry and wet thermometer, fill in the same value. The air pressure is 1014, which records the environmental information. Secondly, there are the additive and multiplicative constants of the instrument, which are related to your instrument specifications and hardware. In fact, you can directly obtain them from the instrument. If you cannot obtain them from the instrument, you can refer to your identification certificate. Every year, we calibrate the instrument, and the verification certificate also indicates the values of these two constants, because the verification of these two constants is an essential verification item. We will fill it out here. If you don't know or don't need to correct it, you can fill in 0. Why do we need to input this information into the software? One is for the convenience of everyone. There is no need for you to record on paper or notebook. Secondly, it is convenient for us to make corrections later on. There is one thing to note here, which is that we record the environmental information on the software and export the data. When we go back to the internal adjustment, the software will also make corrections based on the information you record. If you don't need such high accuracy, then you don't need to fill in this and don't change it to keep it as default. If you need to fill it out, you can use a thermometer to measure the actual temperature, pressure, and the actual multiplication constant. Secondly, if you make corrections on the software, there is no need to make corrections on the instrument. If there is an atmospheric correction setting on your instrument, keep it in the default state, which is no correction, because the software and instrument only have one place to correct it. If corrected on the instrument, the software will remain default. If corrected on the software, the instrument will remain default. Do not correct twice. Then, we will record the height of our instrument and the height information of the prism. The height of the prism can be reported to you by the runner, or you can go and measure the height first before returning. The height measurement is relatively simple, so we can use a tape measure to measure it. The height of this instrument is 1.586. If the prism is high, our rear view is 1.24. For the front view, I can input any value because we are demonstrating, and the prism is directly placed on the ground. Click OK, so we can start observing. At present, the software defaults to 4 measurement sets, as according to the national 3rd and 4th level standards, there is no clear quantity for this measurement set, so we follow the default. Start measuring the first target, and observation is relatively simple. Just aim at one target and observe its 4 measurement values. If you are observing manually, you can also separate it and observe it first, then look forward, and then look back and then look forward, one by one. Alternatively, you can first observe all the backside measurements and start measuring the second target. The current measurement loop has been completed. Start measuring the third measurement loop and start measuring the third target. The current measurement has been completed, starting to measure the fourth measurement, and starting to measure the fourth target. All measurements have been completed. Okay, we have completed the observation in the back view, and then we will proceed to observe in the front view. Slide to the front view interface and click to start measuring. Start measuring the first target. The current measurement loop has been completed. Start measuring the second measurement loop. Start measuring the second target. The current measurement loop has been completed. Start measuring the third measurement loop. Start measuring the third target. The current measurement loop has been completed. Start measuring the fourth measurement loop. Start measuring the fourth target. All measurements have been completed. Okay, all the measurements of the backward and forward views have been completed. After the observation is completed, click on the station adjustment again to determine a result of 12.33 after the front view has been reduced. Then, look at the front view 17.082 again, and it is considered that the observation is complete. Finally, before moving the station, it is necessary to record another piece of information, which is to record the height of the instrument again. Then, when two prisms are moving the station, their prism heights need to be recorded again without any difference. Why do we need to record it twice? Because according to the requirements in the specifications, if the height before and after measurement exceeds 3 mm, the software will remind you. Your data can still be exported normally, but it will only remind you. Because your height changes too quickly, It indicates that your station may be an installation problem, and the accuracy is not ideal. You can consider observing this station again, and then click OK. In this way, once the observation is completed at this station, it can be moved to the next station. After the observation is completed, we can click on the Elevation Traverse Data Export in the management interface to select the previous measurement station and then export it. In this way, the data is considered exported. Next, let me demonstrate to you the operational process of setting up a station at each point. What I just demonstrated to you is setting up stations at different points. I need to create a new project to set up stations at each point, just for one-way observation. Because I am just showing you, if you have certain accuracy requirements in actual work, I suggest that you choose this opposite observation. I won't go into detail about the process of selecting control points and creating a new route, as I mentioned in the previous video. Then, when you come to the measurement interface, you still need to create a new measurement station and check the endpoint. Okay, as you can see, the biggest difference between setting up stations at each point and setting up stations at intervals is that there is no switching between the front and back view pages, because setting up stations at each point is directly set up on one control point to observe another control point or encrypted points for observation. Therefore, it does not distinguish between front and back view, so we can directly observe. The observation process is still the same as before. Before observation, we need to input the current environmental information and the multiplication constant of the instrument, measure the instrument height and prism height. After recording, we can start the measurement. Everything else remains the same as before, and the above is the process of observing the triangular elevation in the Traverse Assistant app. In the next segment of the video, I will demonstrate how to perform adjustment on the surveyor's adjustment after exporting elevation line data, calculate the elevation difference data between each control point, and perform the overall triangle elevation line adjustment process. The following content will mainly explain to you the elevation wire function of our wire assistant. This is about the internal adjustment part of the elevation line, mainly to explain to everyone that if you have completed the field observation, how to export the original data of our field observation elevation line from the app, and secondly, copy our observation original data to the computer. How to use this surveyor's adjustment computer software to adjust your original data. One is to form our original observation manual, and the other is to form the final height difference data we want, which is the height difference data after the final adjustment. These are two major parts. Next, let me explain how to export our raw data on this mobile device. If we have already observed all the data from the current station on this measurement interface, we can also adjust through this station. There is no problem with the station detection. We will export the elevation line data through the management interface. If you are observing an elevation line type project, it must be in this area before exporting. Then, we select the project we want to export, click on Export, and then click Share. This can be sent to your computer through QQ or WeChat. The data is actually stored in our local root directory, where a wire assistant exports files. You can also find it in the form of a compressed file. If you forgot to share it on your computer at that time, you can also find the path I just mentioned in the file manager and share it later. Secondly, after exporting, if we open the compressed file on the computer, we can see that one of the important things to pay attention to is the control point, which stores all the control point information we input and use in the software. Please check if it is empty. If it is empty, It means there is a problem exporting. Secondly, this folder is our route folder. We don't need to open all the station data on the current route. What we actually need to use are the DXH and DXR files for the current route outside. If we confirm that these files are not missing, we can directly open the surveyor's adjustment software. This software is currently available for free trial, and you can directly download it from the official website of ICE Measurement Technology. We choose the electric wave distance and elevation wire function on the surveyor's adjustment homepage. There are two main functions in this. One is to import elevation wire data and display our elevation difference calculation table. One is to display the elevation difference of our route. By the way, it is actually quite simple. At the beginning, we can enter the elevation wire data and click Import to import the two files we just generated, one DXH and one DXR. In this case, I will directly import a calculation example for you because the data I just mentioned is not very intuitive. Let me introduce an example for you to see more intuitively. In this case, we can actually see the original observation data of each station after average reduction, its measurement point, aiming point, and then the meteorological correction data of temperature, humidity, and pressure that we input, the addition and multiplication constants, and the height difference and height difference correction values calculated based on the corrected slant range vertical adjustment, according to the instrument's high prism height. The final calculated height difference value for each of our actual stations is an observation data that has not been adjusted, but has only been corrected by meteorological and multiplication constants. What is the main purpose of this data? We can click on the height difference calculation table below to export it to the desktop. The main purpose of this data is to, let's create an original observation manual that can be printed, signed, and reported, or anything. This is one of our roles. Secondly, it is to allow us to check if there are any issues with the final observed data, such as the height difference you actually observed. Although you do not know an accurate value, you still generally know it, such as its positive and negative values, and who is higher and who is lower. So when you look at the positive and negative values, or roughly a height difference value, you should also be able to see if there is a problem with the measurement, because software can only guarantee that in your current measurement, each measurement set will not exceed the limit, and then between measurements will not exceed the limit. However, software cannot guarantee that you will not make mistakes, just like when you set up A1 to aim at N1, but what you are actually aiming at is N2. That software actually does not know. The software can only guarantee that the data within your single testing station will not go wrong, but if you aim at something that is not actually that target, or if you have not aligned or leveled it, the software cannot detect it. So you can check and double-check here to see if there are any issues with your original observation data. Secondly, if there are no issues, we can import our DXR file into the observation data of this route. If you look at this data, you can also see that there are two routes in total, one from N1 to N2 and one from N2 to N3, and then the height difference between the two routes is finally formed. What is the purpose of this? I have just explained this to you. If we have a triangular elevation line, assuming we have 4 points from 1 to 2, from 3 to 4, they are actually the 4 points we need to participate in adjustment. The first 4 points are control points, and the second and third points are encryption points. Therefore, we need to participate in adjustment for these 4 points. When creating them in the app, we will actually create 3 routes, 12 is a route, 23 is a route, and 34 is a route. So, in this interface, we will actually form 3 routes, and if these 3 routes are to be adjusted later, we will definitely need to do so. Only then can we know what to do if we want to adjust the elevation of point 2 and point 3, which is already within this area. This is a correction for the non-parallelism of the water level. As you can see, it will be corrected based on your starting latitude and ending latitude. Finally, the N1 to N2 route, which is the height difference from point 1 to point 2, will be calculated, which is 20.50 40.60. At this point, we can export this and export it. After exporting, we can come to our leveling network adjustment interface. On this interface, this requires logging in. In the leveling network adjustment interface, we can create a new project. If the elevation is known, we can import it directly. The file in our control point can also be inputted directly. For example, our first point is designed with an elevation of 100, which is our 2 control points. For our fourth point, it is 102, and in the elevation observation values, we can input it directly. We just exported the adjustment file in the trigonometric elevation function, imported it, and then we can calculate the adjustment based on your trigonometric elevation level or the owner's requirements. That is to say, if we want to perform the adjustment, we need to first import the root observation data in the electric wave ranging function, and then export the adjustment file. Then import the adjustment file into in the height difference observation value of the triangulation adjustment. You can perform the adjustment here. If everything goes well, it is our triangulation height function. Thank you for watching.